It's Terry Dennery, the math works. So our last video, we finished with this, and it was kind of the idea based on vertical takeoff, the ascent. If we can define that trajectory, we should be able to figure out the thrust, and based on kind of the aerodynamics of the propeller, we should understand, what our motors that are going to drive propellers need to do to essentially ramp up and get the speed of the propellers to generate that thrust, right? And I'd say that it was a good plan, and I'm still happy with the plan. We are going to execute that plan, but as I dived into you know recording what I thought would be one video, I realized, oh, there's a lot of really interesting stuff going on for that, and that's what this video really will be about, is to just kind of explain things that we weren't quite thinking about as we produced that last video. Now, I'll begin with just kind of a few corrections, right? And some of you may have noticed this when I did the previous video, but I didn't have that there. This is where we kind of finished. And so what we calculated is based on gravitational load as well as acceleration and multiplying that by the assembly mass of the full vehicle. Well, this is the thrust required of the entire vehicle, right? And so let's just put that gain back in place. And it's the basic idea, well, we have 40 units, so let's take that number, divide by 4, and that's what we're going to require out of each of our propulsion units. Okay. Now, this, I'll just say, -1. Well, why is that? And I can kind of get into kind of how SimScape multi-body works and all that kind of stuff, but I'll just say that the direction can be a little more arbitrary than you think. Okay, and I'll also add, it's good to be prepared to add a -1 every now and then, as a multiplier. All right, so I'll just say from kind of trying it out and just kind of working it, I realized it needed to be a -1. We might get a little bit more deeper into that topic at some point. Right. So anyways, let's go ahead and hit run. Go. Hit run from here. Okay, so that's the propeller. This is essentially the test we're doing. So we got that case, we got the shaft, and we got that propeller, and we spin it up, and it's spinning pretty fast right now. The calculation's done, and this is simply playback at this point, so we just stop it right there. Right. And let's come in here, and let's see that we kind of do okay, but boy, we got this kind of crazy oscillation that takes place at the beginning. And the basic idea of the controller is, well, we calculated the load needed in Newton meters, and we're even applying feedback so that we take the commanded velocity, we compare it with what's measured, and we operate on the difference, which we call the error with the PID. All right, so that's classic feed forward and feedback working together. Right. And it turns out our feed forward, is missing a really important piece. And I'll just kind of go in here and perhaps be able to kind of make my point with this. Is that this is our load, and based on this parameter that we designed called lift to drag, where our drag is really the drag on the propeller. That we compared it to the thrust, and that this is all really about aerodynamics at this level. And there's nowhere in here this term which is taking the inertia of the propeller and figuring out how many Newton meters I need to accelerate it to bring it to the velocities I need it to operate at. Right? And so I'll just say that the inertial loading of the propeller itself is now properly being accounted for. Now, implicit in kind of our design was, well, we think that those aerodynamic loads are be much higher than the inertial loads of merely accelerating the rotational frame of that propeller, right? And I believe that probably is true. And I'll just kind of dive into the model there right now and just kind of acknowledge that at some point you need to start caring about things like material density, and that you actually start choosing propellers based on what they're made out of, and that's why they're made out of things like graphite and various other kind of materials that can be designed with very, very high strength and be very light in their overall mass. And the industry of aerospace in general is very attentive to this sort of thing. So anyways, updating this, we'll see that, well, we got a 55 kilogram propeller. I'm not sure what the real material densities are, and certainly they make these things hollow, and so they're not fully solid, and all kinds of things can be done to optimize the mass. But I'll kind of go for the idea that, well, probably something like divided by 20 would be good. So let's apply that, and let's update that. And I'm not sure if this is possible or not. That'd be a little bit over 5 pounds. It might be possible. And for right now, it's simply, what we hope is available, and we'll go out and we'll get vendors, and we'll figure out what truly can be done. Right. So I'll do that, and let's go here. Even the shaft needs to be kind of modified. So okay. So let's rerun the test. I'm just running the scope right here, and we'll see that that fixed that problem pretty well. Right now, this next part is a little subtle. Right? And it might require an additional video. And I think in real life, you probably need to do what I'm going to suggest. Okay. But that we're kind of, we get used to this idea that, oh, I can turn on forces and turn them off. And essentially I can have step commands for things like force. Well, not if you're achieving it by spinning a propeller, and it really kind of puts constraints on the next level of derivative. All right, and so what it says is you can't have discontinuous acceleration. Turns out because you're going to use motors to do this, and you're going to presumably discontinuously apply voltage, it needs to go up an even that higher level, and it needs not only so the sequence is position, velocity, acceleration, then comes jerk, and then comes snap. And I forget what goes beyond snap, but somebody knows that stuff, and it is important. And I'll just say that the constraints really go all the way up to the snap level. And so anyways, but we got something that kind of works, and it kind of works because PIDs are these remarkable algorithms that can take an impossible request, like a step, and give you a reasonable representation of that. So it ramps up finitely, and generally you pay for it with a little bit of overshoot, and then you decide if I'm okay with each of those. But anyways, so I think what we'll do here's what I think are the next two videos. I am going to spend a little bit of time with MATLAB and figure out if I can craft or design trajectories where I'll have finite snap, and then we'll attach these to our vehicle, and we'll make sure that that vehicle can go from 0 to 2,000 meters in 100 seconds. All right, thank you.